Hey guys, I'm going to do this video old school. So I forgot my iPad pencil at school, I think. So I used to make all my videos like this, so it shouldn't be a big deal. But it also gives me a chance to kind of show you how I might use the reference materials. So let's do it. Our essential question is, how is Cavallari's principle helpful in understanding the volume formulas for solids? Okay, so we noticed Cavallari's main principle was if 3 of these would equal the can and 2 of these equal the scoop, then his principles would have helped us understand that the scoop plus the cone equals the can. Also, in that same way, we could subtract, right? We could subtract a cone on both sides. And so Cavallari's biggest principle that we learned in 11.4 was that we could use algebra to say that a scoop, if we were solving for the scoop, we didn't know it, we could take the can and subtract the cone. Very, very interesting. So this was a way that scholars could find the volume of a hemisphere without really finding the volume of a hemisphere. Cavallari's principles also tell us 2 things: that if, 1, you have the same cross-sectional area throughout, many of you wrote this on your THRUG, throughout, and 2, you have the same height, then logic and reasoning require that that has to have the same volume. If you think of it slice by slice. So looking at our vocab terms, it says a prism is blank if one or more faces are not perpendicular to the base. So if we have a prism, so here's a prism, we can also think of a prism like this. If one or more faces is not perpendicular, so I don't want to go perpendicular, I want to go slanted. Okay, so what if I do? Slanted over. See how I still have a prism stacking the same shape over and over, so I still should have an object. But if I don't, then the special word for that, and you could Google this, would be instead of a right, it would be an oblique. Interesting word. And that's where Cavallari's principles come in. Even if I don't know the volume of this object, but I do know the volume of it being a right prism, meaning it makes this right angle with the base, then if I know the volume of this, then they have to be equal if they have the same cross-sectional area throughout, right? All right, blank describes the relationship between the volumes of 3-dimensional fingers. They have the same height and the same cross-section. Yeah, that's what we just said. That's our Cavallari principle. I'll call Cav's principle. Nice. Okay, and the last one, a great circle. So we talked about this a couple times today. A great circle is the largest diameter or largest radius circle of the cross section. And it marks the equator, halfway between the 2 hemispheres, northern hemisphere and southern hemisphere. Nice. Okay, lesson 11.1, we see the faces of a polyhedron. Euler's formula from our notes is this formula. And we can total up the faces and the vertices and the number of edges, and it should match this formula. The cross-section of a plane and a convex polyhedron is a polygon, and rotating a polygon about an axis forms a 3D shape. Okay. So here, if you had 5 faces, so see at the letter F, they substituted a 5, 9 edges. So the letter E, they substituted a 9. And notice they used algebra to solve for V. This prism has 6 vertices. We noticed this anyway from our picture. Sweet, right? Now, doing some more examples in lesson 11.1, it says a pyramid has 6 vertices, okay? 6 vertices, so V is 6 and E is 10. How many faces does it have? So what is F? Using this formula, F plus V equals E plus 2, we can substitute V as 6 and E as 10. So on the right, we get 12. And if we subtract 6 on both sides, we get F is 6. So how many faces does it have? We get the answer 6. So how does that make sense? Well, notice we have a face in the back, 1, 2, and then this face in the front, 4, 5, a face for each side of our pentagon. And then I didn't count the bottom or the base. That'd be that 6th one. So even if you have trouble seeing in 3D with the picture, Euler's formula provides an opportunity to make sure that we get the right answer. Visualize a plane intersecting a pyramid, this is a pyramid, parallel to the base. So if we visualize and we go parallel to the base, we said in class, if you go parallel to the base, you're just going to get another base, right? So what will this cross section be? Another smaller pentagon or 5-sided shape. So when you go parallel to the base, you get another base. Parallel to the face, you get triangles in a pyramid or rectangles in a prism. Let's describe the 3D figure shown by rotating this rectangle. Okay, so hopefully you can kind of see. If we spin this around and around and around and around, we spin, 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 we're gonna get a cylinder laying on its side. So we get a cylinder that has the radius of this length, that would be the radius, and the height would be the, whatever length this is, the length of that, that's a cylinder, right? So describe it, it's a cylinder. Okay, number 8, can a polyhedron have the same number of faces, edges, and vertices? So let's make this up. Okay, so if we have this formula, the formula for 8, can it have the same number of faces, edges, and vertices? So let's just pick a number like 3, 3, 3. And we're like, no. So is there a number, let's say we put 2, 2, 2, 2. Ooh, that works. So the answer would be yes if the faces and the edge and the vertice are all 2. 2, 2, 2, 2, 2. But let's take a look at that. Can you have 2 vertices? That doesn't make sense. So the answer would be no. No, because I can't have just 2 vertices. So this formula works if these numbers are greater than, it's got to be a 3D shape, right? If large enough numbers, let's just say. That's not a 3D shape, that's just a line. So if you only had 2 vertices, that's just because it only works at 2, and that's not a 3D shape. Okay, and in our textbook, it'll tell you like the minimum number you have to have. So to have a 3D shape, you'd have to at least have 4. So I think vertices, V has to be at least 4. V has to be greater than or equal to 4. Or else it's not a 3D shape, so it can't be a polyhedron. All right, now for 11.2, it says Cavallari's principle states that the figure with the same horizontal height and same area at each cross-sectional area have the same volume. We would agree. And so they worked out the volume of this prism and the volume of this cylinder. Do these cylinders have the same volume? Absolutely, because they have the same radius, which means they'd have the same cross-sectional area, and they are at the same height. So based on that principle, then it would be yes. Yes. All right, so using these principles, we will answer question number 9. It says find the volume of each figure, round to the nearest tenth. Okay, so we do, are you gonna fall for that? You knew that was coming. They gave you the diameter is 30, so the radius is half of 30, or 15. So the volume is the area of the base, which is pi r squared, times however high you stacked. Looks like we stacked these horizontally. So pi, 15 times 15 times 70, and our answer will be millimeters squared. Okay, so I'm just gonna pull out my calculator here. All right, so no, I don't need an add. So pi times, what was the radius? Yeah, 15. 15 times 15 times 70. I get 49480.1 millimeters cubed. I said squared, but I meant cubed. Okay, there you go. 10, the volume here, so I'll use a little space up here. Volume is pi r squared h, so that'd be pi 3 times 8. Pi times 3 times 3 times 8. 6.2 yards cubed. All right, what does the expression 3/4 xyz represent for the prism shown? So we notice that the volume here would be the area of our base times however high, and it looks like we stacked these triangles horizontally. Okay, so the area of our base is a triangle. So 1/2 base times altitude times height, because it is a triangular prism. So we have 1/2, our base is 1/2 z, altitude is 3y, and x is our height. So we get 1/2 times 1/2 is 1/4 times 3, so that's 3/4 x times y times z. Yeah, that I can put in any order. So I'm multiplying, you can multiply in any order. So what does this expression represent? It's the volume. All right, question number 12, last one in this section. It states, Malia pours wax in a mold to make candles compare. So we're trying to find out which one's greater, the left, the right, or are they equal? So the one on the left, base times width times height, right? 21 times 7 times 18. So let's do that. 21 times 7 equals times 18 equals 2646 centimeters cubed. And then this shape, which is a very interesting shape, isn't it? It looks like a hexagon. I don't know if it's a regular hexagon. I'm assuming, I guess it is. It definitely is a trapezoid. Okay, so so it's a trapezoid that's 5, 16, and an altitude says it's 14, so that would be 7. Okay, so let's just say it's 2 trapezoidal, which is right out of our foldable, and then just double our answer. Let's do that. Okay, so it's 1/2 b1 plus b2 times our altitude times our height. So 1/2 5 plus 16 times 7 times our height of 18. So 1/2 And that's 21 times 7 times 18. And then remember, I'm going to multiply everything by 2. So that would be great because that's the trapezoidal prism, but then I got another trapezoidal prism back there. So I'm going to double it. So I get 21. 21 times 7 equals times 8. Ooh, did that wrong. 21 times 7 times 18. 21 times 7 times 18. Third time's the charm. Okay, 2, 6, 4, 6. And we just keep, interesting, they're exactly the same. So even though they're a different shape, they are made up of the same amount of space. All right, check out the next video for sections 11.3 and 11.4.